Alright, gang, here we go. This is for Chem 1, Unit 11, Part 1. We're talking about solutions and solubility. Lots of stuff. Buckle down. Use the restroom before it's too late. Here we go. Alright. Solution formation. So we've already talked about this a little bit, but solutions are homogeneous mixtures. Homogeneous mixtures. So that means they're the same throughout, all right? And they're made up of a solute and the solvent. The solute is the substance that's being dissolved. The solvent is the substance doing the dissolving. So if you have a solution of salt water, your solute would be the salt or the sodium chloride, and then the solvent would be the water. Okay? Because the salt, or the NaCl, is what's being dissolved, and the water is the thing that is actually doing the dissolving. All right, so there's two types of mixtures that I want you to know. All right, and mixtures are not the same; they're heterogeneous. Okay, as opposed to the homogeneous mixtures. And a suspension, they might start out the same. Okay, and they're homogeneous, they're the same throughout, but their particles, the solute that's being dissolved in there, is so large that they settle to the bottom. So if you take, a big container of mud or sand, mix that thing up, it's going to be all the same throughout at first, but if you just let it sit, then it's just going to settle down to the bottom. And notice you have to have a little bit of patience here. See the patience there, right? And there should be like a little level for the water. So if you've ever been to the beach and gotten, filled up, a bunch of scooped up some water and sand, you mix it up and it's all a suspension. It's all mixed in there. But if you just let it sit, all the sand will settle to the bottom because those sand particles are too big to be suspended indefinitely. All right, so that's why we call them suspension. All right, we also have colloids. All right, and colloids are mixtures, but their size of the particles that's being dissolved are in between solution particles and suspension particles. So they're somewhere in between those two. And so because of that, they have an interesting effect. They have this thing called the Tyndall Effect that we'll look at here in a second. The Tyndall Effect is what we use to diagnose colloids, because a solution will not exhibit the Tyndall Effect, but a colloid will. All right, so some examples of some colloids are like smoke and milk, fog, jewels. All right, these are all colloids. All right. Yeah. So anyway, so like smoke, for example, is solid particles of carbon and soot being suspended in air. Okay, and they don't settle out; it just kind of gets spread out. You're in milk, like what's in the fridge, cow's milk, whatever, is just fat molecules and other things that are suspended in water. Fog is water vapor that's suspended in the air, so on and so forth. All right, so the Tyndall effect, that's that thing we were looking at earlier. The Tyndall effect occurs when you put light through your substance here, your mixture, and you can actually see the beam of light as it's traveling through. So here we've got this flashlight, and it's being shined into a solution. So I think this is salt water, and you can see that you can't see this beam. You see a bright spot here where it transitions from the glass to the liquid, and then on the other side again you see this bright spot, and then but you can clearly see the beam of light as it travels through the suspension over here. All right, and then you've got on the other side. Here's another example: is cars traveling through, a fog or a rainstorm. Okay, you see these. You can actually see the headlights, the beams from the headlights being dispersed by the Tyndall effect as it's traveling through this foggy or rainy day or whatever, night, whatever it may be. All right. Now, Brownian motion is another thing that I need you to know. Brownian motion occurs when you're observing particles of a suspension or a colloid under a microscope, and the particles appear to be moving quickly and randomly. And this was discovered by this guy named Brown. And he took a microscope and he was looking at, I can't quite remember what he was looking at, right? But he was looking at something, and he saw these particles that were in here, okay? And these particles were not all moving in the same direction, and they'd kind of slow down and speed up and slow down and speed up and move kind of all randomly inside the microscope. And he could see that these guys were just moving like crazy. And so he came up with, there's been lots of different examples or lots of different explanations about why this occurred. And then eventually, when subatomic particles and particles that were smaller than what you could see with an optical microscope were theorized and developed, it became clear that these random motions of these particles that you could see with a microscope were actually occurring, these changes in direction, because small particles that we could not see were running into it. And it's all based out of the kinetic molecular theory. It's just because you get these particles you can see, and then there's these little individual particles that are too small to see, and they're bouncing around hitting these smaller particles, and so they kind of move around all over the place. And so this was coined as Brownian motion because he was the first one that kind of witnessed this motion under a microscope, right? And so this is touted as a proof that anybody can see in just a regular laboratory with a cheap microscope that small molecules do exist, right? And if you click this YouTube video, they do a great job showing Brownian motion under a microscope, and you can kind of see it going on, right? Now, definition of solubility. Solubility is defined as the amount of solute that can be dissolved in a given quantity of solvent at a specific temperature and pressure to produce a saturated solution. All right, so what all does that mean? Solubility is essentially how much can be dissolved, all right? How much can be dissolved. Right, that's essentially what we mean by solubility, how much can be dissolved. And specifically, we're looking at a specific temperature and a specific pressure. All right, and so the units for it can be a couple of different ways. It could be grams of solute per 100 grams of solvent, or this one is probably most common, grams of solute per liter of solvent. So let's just do a little couple practice here. It says the solubility of carbon dioxide in water is 0.54 grams per liter. How many grams of carbon dioxide would be dissolved in 250 milliliters of water? All right, so we've got, we're just going to do some dimensional analysis. You guys should all be pros at this now. So 0.54 grams per liter, and this is essentially saying that we have 0.54 grams in every 1 liter, all right, and it says how much would be dissolved in 250 milliliters, so how many grams? So we just need to get rid of the liters, all right, so we're just going to multiply it by liters here. If we can multiply that by liters, the liters will cancel. Well, how many liters is it? Well, it's 0.250 liters, right, because there's, you divide it by 1,000, so 0.250, all right, so you take 0.54 times 0.25, you get 0.135, 2 sig figs, so 0.14 grams, grams of CO2, all right? So that's how many grams of CO2 you can dissolve in 250 milliliters of water. All right, how many moles of CO2 are dissolved in 1 liter of water? All right, so same idea here. We got 0.54 grams. We need to convert those to moles. So it's 0.44 grams per 1 liter. All right, so we're going to get rid of that liter by multiplying by our liter. So 1.0 liters, so our liters cancel. And then we got to convert our grams to moles. All right, so we got grams of CO2 in the bottom, moles of CO2 up top. Put 1. All right, so we got carbon dioxide, right? So we got 1 carbon and 2 oxygens, 12.01 and 2 times 16. All right, so we say 12.01 plus 32, and we get 44.01. All right, 44.01 grams per mole. There's our molar mass of carbon dioxide. So we'll put 44.01 in the bottom. So we take our 0.54 divided by our answer, 44.01, and we get 0.012269. How many sig figs do we want? We want 2 sig figs, so 0.012 moles. 0.012 moles of CO2. Boom. Bob's your uncle. All right. What would the solubility be in moles per milliliter? All right. So this is kind of fun. So we're going to do our 0.54 grams for every 1 liter. We got to convert our grams to moles and our liters to milliliters. All right. So we can do it either way. So let's see. So we'll go grams to moles first. So we put, it's the same step as what we just did here. So grams go on the bottom, moles go on the top. So we put 1, and 44.01 goes down here. All right. And then from liters to milliliters. All right. So we got to put our liters up here. And for every 1 liter, we have 1,000 milliliters. So we'll put 1,000 down there. All right. And so we get 0.54 divided by 44.01 divided by 1,000. And we get, again, 2 sig figs, so 1.2 times 10 to the minus 5th. 1.2 times 10 to the minus 5th. And our units would be in moles per milliliter. There you go. Pretty sweet. All right, saturated versus unsaturated solutions. All right, so a saturated solution is a solution that contains the maximum amount of solute that can be dissolved in that solvent at the given temperature and pressure. So if you have ever made Kool-Aid, okay, and then we did this in scout camp when I was a kid, and so we took Kool-Aid, right, and they had this like just big tub of sugar on the table, and we just dumped in our Kool-Aid. We dumped sugar in our Kool-Aid until no more sugar dissolved anymore, and we just got a pile of sugar at the bottom that wouldn't dissolve anymore. And so that was a saturated solution because we've dissolved all of the sugar that could be possibly dissolved in that water, and then what was left was just the extra that couldn't dissolve anymore. So we'd made a saturated solution. So for example, if you took 36.2 grams of sodium chloride, or 36.2 grams of sodium chloride can dissolve in 100 grams of water, all right, at 25 degrees Celsius. So if you had 100 grams of water and you put in 36.2 grams of sodium chloride, you'd have a saturated solution. Anything more than that wouldn't be able to dissolve. So if you put 37 grams of that sodium chloride in there, the additional 0.8 grams would not dissolve because it's already reached its saturation point and you can't dissolve anymore. All right. So you've reached equilibrium between the solution and the undissolved solute. And so we've got this saturated solution. Remember, equilibrium, we talked about this before. We talked about dynamic equilibrium when we talked about phase changes as the gas goes to the liquid and liquid goes to the gas. All right, so at equilibrium, we've reached this point where our solute particles are being dissolved, but at the same time they're falling out of solution. All right, so an unsaturated solution is a solution that contains less solute that can be dissolved. So if we, that salt, we could dissolve 36.2 grams. So anything less than 36.2, if you put in 35 grams, you would be an unsaturated solution because it could still take 1.2 grams more. Okay, and so here's your unsaturated solution. Over here, less solute, notice, versus your solvent, and then over here, you've got your saturated solution, and so you've got your solute particles in here, but you've also got a nucleation here, and so this nucleation, this is occurring as these things are hitting each other, and then they're falling out of solution, and then redissolving, so you get these particles that settle to the bottom that can't dissolve anymore. All right, so a supersaturated solution, now these guys are super interesting. A supersaturated solution is a solution that contains more solute than it can theoretically hold at a given temperature. All right, so it contains more solute than it can theoretically hold at a given temperature. So you can crystallize this supersaturated solution or make any of the extras fall out of solution. This is the phrase used. They fall out of solution because they literally fall down. And so there's the crystallization, and it can be initiated by you can just add like a very small crystal called a seed crystal, and then it kind of gives them that nucleation point, and they can start to fall out. All right. We also use these hot packs. If you've ever seen these reusable hot packs, and they've got they're little plastic dudes, and they've got this solution in it, and then they have like a little metal snapper, and you can snap that metal thing, and it gives it that energy needed, that nucleation point to just fall out of solution. And then it crystallizes, and as it does so, it heats up, right? And then you can actually, so it keeps your hand warm, whatever, in the wintertime, and then you can take that same thing and you can stick it in in boiling water in order to make it usable again. And so the way you make a supersaturated solution is by playing around with the saturation or the solubility. Okay, so at room temperature, we can have this solvent, and we've put in this solute down here, and so that's what's going on right here. And so you've made it saturated, so it's holding as much as it possibly can. Now, if you heat this guy up, it's going to increase the amount that can dissolve in here. Okay, so by heating up the solution, you've increased the amount of solute that can dissolve in your solvent, and so you've added more and more and more solvent. So notice that now we're at a higher temperature. See the fire down here? It's all this fire, and so we got the solute in here. Okay, much more solute. All right, so we've reheated up our solution here. So we're at a new saturated, we're still at a saturated solution, but because we're at a higher temperature, we can dissolve much more in there. Then what you do, the trick is to make it supersaturated, is to take this same solution and then let it cool back down to room temperature very slowly. All right, and if you let it cool down very slowly, then you get a solution, but it's holding more solute in solution than it technically should be able to. And so you've tricked the solution into becoming supersaturated. Okay, and so by adding a little seed crystal in here, like what we were talking about earlier, or by giving it that little metal popper dude, all right, it gives it just enough energy, a little oomph, to make it start falling out of solution. All right. Here's the solubility curve. Okay, so here is our line of our saturated solution. So here's our temperature, and then here's our solubility, grams per 100 grams of our solvent. And so this line shows us we can figure out what our temperature is. You know, say you're at this temperature here, and you can figure out exactly what your solubility is based on your curve. And as you increase temperature, you can see what happens. And notice that for this specific particle, whatever we're talking about, as we increase our temperature, our solubility tends to increase. All right. If we're above that line, if we're somewhere up here, we're in a supersaturated solution, and if we're somewhere down here, we're unsaturated. Okay, so here's a solubility curve for a whole bunch of molecules all put together. So here's sodium nitrate and calcium chloride, lead nitrate, etc. And we can see that generally, as our temperature goes up, most of these things increase. Now notice that there's some oddballs, like the cesium sulfate here. He's an oddball. He started with higher solubility, and then as temperature increased, his solubility actually went down. Notice that some guys, their solubility increases dramatically with temperature, like calcium chloride. It's really exponential. Look at this guy; it shoots up here. But like lead nitrate is pretty much linear, and sodium chloride is hardly affected at all. So every single molecule has its own, or every single compound kind of has its own solubility curve. So in order to use these, you actually have to have a solubility curve for that particle in that solvent. All right. A couple last things here we got to talk about in part one. This, I told you, it'd be a long video. All right, electrolytes versus non-electrolytes. All right, electrolytes are substances that dissolve in water and conduct electrical current. All right. So so if it dissolves and it forms ions, okay, and they turn into charged particles, all right, so you're dumping sodium and chlorine in there, and it splits up into Na plus and Cl minus, and you get, because of this ionization, this change in your charges, you actually get the ability for it to conduct electrical currents. Non-electrolytes are substances that when they dissolve in water do not conduct electrical current, all right, so any insoluble ionic compounds, so you can go back and look at your solubility rules, all right, or molecular compounds. So like sugar is a non-electrolyte. It dissolves in water, but it is not ionic. It's covalent, all right, and so because it doesn't break into these charged components, it doesn't change, or it does not conduct electricity. So this would be like sugar. It would be a good example of that. All right. All right. Last little bit here, factors that affect rate of solubility. So notice that we're specifically here, we're talking about the rate of solubility. So these two things do not increase how much will dissolve. They only increase the rate at which it will dissolve. So how fast will it dissolve? So we can affect the rate of solubility by two main ways. We can agitate it. Okay, we just pick it up and call it names until it's your mom was ugly and your dog didn't like you. No, I'm just teasing. So that doesn't work. Really, we're talking about stirring it. So by stirring it, we can get it to mix up faster, and so the solubility, we reach this the point at which it all dissolves at a much quicker rate. All right, so the solute and solvent interact more often, so dissolving occurs faster. All right, so that's really all it's about, is just being able to get these solute and solvent particles to intermix with one another. And when that occurs, the solvent can surround the solute and break it apart. All right, and then we could also, by changing the surface area of our solute, if we increase the surface area, then we increase the rate at which these two things can mix, and so therefore we increase the solubility. So by taking our substance instead, so if you imagine taking a salt cube and putting in water, all right, it'll eventually dissolve, but if we took that salt cube and crushed it up and then sprinkled it in our water, it would dissolve a whole lot faster. All right, so those two are the main ways that we can increase the rate of solubility. All right. Now, there are two ways that we can affect the amount that can be dissolved. All right. Temperature, we've already talked about briefly when we talked about our solubility curves here. We noticed that as we increase temperature, our solubility increased generally. The cesium sulfate's an odd duck, but generally, if we increase temperature, we increase the solubility. So increase in temperature increases solubility because the kinetic energy increases, so their collisions occur faster. and then contact them more often. All right, and so it increases two things. It increases the rate of solubility, but it also increases the amount that can be dissolved. All right, and so so a temperature plays a big role when we're talking about solubility. All right, now there's a few exceptions. We just looked at cesium sulfate, odd duck. Okay, his solubility actually decreased with an increase in temperature. Now, so that's for solids. Now, the interesting thing is all gases, okay, this guy here, this is important, okay, all gases are more soluble in cold temperatures than in warm temperatures. So if you think about your pop, if you've ever gone to your fridge, okay, and taken out a Dr. Pepper, I like me some Dr. Pepper, you open up your Dr. Pepper straight out of the fridge, take a sip, and it's got that nice crisp carbonation feel to it. Whereas if you go to your pantry and you pull out a Dr. Pepper that's been at room temperature and you pop it, you notice that it's got significantly less carbonation. And that's because there's literally less carbon dioxide that's dissolved in the room temperature Dr. Pepper than in the fridge temperature Dr. Pepper. And there's less carbon dioxide that's been dissolved in it, and so therefore it's less carbonated, and it's got less of that crispness. Now, so all gases are affected this way, which is really helpful. So all gases are more soluble in cold temperatures than in warm temperatures. And essentially that's because these gases are more or less likely to have enough energy to break the intermolecular forces if they're colder. All right. Another way that we can affect the solubility amount is by changing the pressure. Now, the pressure does not affect solids or liquids. All right, and we can change the pressure all day long on a solid or a liquid, and it's really not going to change our solubility. It has a humongous effect on the gases. All right, so if you increase pressure of a gas, it's going to increase the solubility dramatically. All right, so once again, you take that Dr. Pepper out of the fridge and you pop that guy open, and it immediately goes. That's because that can is at a higher pressure generally than the outside air. So when you pop that guy open, you're literally making those pressures equal, and gas is escaping from your can. All right, so it's got a higher gas pressure. Now, not only that, but you've got specifically with carbonation, we care about the carbon dioxide. So by popping open that can of Dr. Pepper, you're releasing the carbon dioxide that was stored in that can. All right, and so that leads us to this guy here named Henry. Henry's law states that the solubility of a gas is directly proportional. Okay, directly proportional to the partial pressure of that gas above the liquid. All right, so in our room atmosphere right now, right, we've only got a very small percentage of carbon dioxide. So your carbonation is going to be a really low percentage. Whereas with your inside your can, when they bottle these things, when they bottle your can or a bottle of Dr. Pepper, they have a very high pressure of carbon dioxide. So a lot more carbon dioxide can be dissolved. So it's not just the overall pressure that's important; it's specifically the partial pressure of the carbon dioxide that's important. All right, so if you increase that partial pressure of carbon dioxide, then you'll be able to have much more carbonation in your solution. All right. As another application of this is the idea of divers getting the bends. Okay, so like when divers, if you've ever heard of the bends, the divers will, they're breathing in nitrogen and oxygen mixture, and so as they go down deeper, the pressure increases. That makes sense. As you go down in water, the pressure increases, so the amount of nitrogen and oxygen that's dissolved in your blood goes up dramatically. All right, as you go down in pressure, and that just follows this idea of Henry's law. Now the problem is going down is not such a big deal. Your blood can handle having extra oxygen dissolved in it. Now the problem is when you come up quickly, the solubility will decrease, and because the solubility decreases, oxygen can escape from your blood and form literal air bubbles in your bloodstream, and that's really bad. Okay, we do not want extra gas bouncing around in our blood vessels, and when that happens, you can get joint pain or just general rashes and weird pains and stuff like that, and it's called the bends. And so when divers go down deep, they actually have to, there's the main way that they counteract the bends is by just coming up very slowly, just little bits at a time. And so by coming up the little bits at a time, they allow the oxygen to bubble out but then escape, and they don't let and the nitrogen as well, and they don't allow it to bubble up and form big pockets of air in their bloodstreams. All right. The other way that they handle it is by, if they, for some reason, there's an emergency and they have to come up very fast, then they put them in a big pressure tank, and they crank up the pressure so it's like what it was down low, and then over days and days they lower the pressure. So these scuba divers are stuck in this tank for days and days. So here we've got solubility of a gas versus pressure. So this is just a way to visualize what we were just talking about. So you've got this piston. Here's your solution, your solvent down here, and your gas particles. As we increase the pressure, we're lowering this guy here, and notice that we get more gases that are soluble in this solution at this higher pressure. And that's essentially what exactly is happening in your pop can. All right. So anyway, lots of stuff we talked about in this video. Part 1 is kind of beefy. The rest of it's not nearly as bad, but part 1's got a lot of really important information. So make sure you spend lots of time doing your practice problems. All right. Let me know if you have any questions, and I'll see you on the flip side.